So I think we left off the conversation speaking about the various pressures, and we started adding some numerical values to some of these pressures, these Starling forces that we were describing. And just to kind of recap that here, we drew out our capillary bed, the arterial end, the venule end last time, and we started describing the direction of each of these forces, okay? So we talked about the interstitial fluid hydrostatic pressure. Remember, the large P represents that hydrostatic pressure, which is that thrusting or pushing force created by the fluid in that space. And we also had the capillary hydrostatic pressure, which is, again, that thrusting pressure that's created by the fluid in the capillary. So these are our hydrostatic pressures. And then we talked about the osmotic or oncotic pressures. These were pull forces that, again, are pulling into the space or the compartment that they're describing. So the interstitial fluid osmotic pressure is a pull force pulling fluid into that space. And then the capillary osmotic pressure is the same thing. It's a force pulling fluid from the interstitial space into the capillary, okay? So you want to be thinking about, and I had a student in a previous class that kind of put an interesting analogy to this, but pretend that you're standing in one of these spots. Pretend that you're either standing in the capillary or standing in the interstitial space, and then think about the force, right? Whether it's a push or pull, and that'll kind of guide you as to where the fluid will be moving, right? So if you're in the interstitial space and it's a hydrostatic pressure, you're pushing fluid out, which must be going into the capillary. So think about you standing in the space that's being represented, where that force is being exerted, and think about what type of force is it? Is it a push force or pull force? And that'll kind of guide you in terms of figuring out where the fluid goes. And we'll practice that a little bit going forward. Now, what we end up seeing and what this schematic shows is that we've got filtration happening on the arterial end of our capillary bed. And then toward the venular venous end, we've got absorption happening. And so when I say filtration versus absorption, we're talking about the net movement on either end here. So the net movement, if we net out those values, we net out our forces, we're going to see that the filtration forces, or the forces that favor filtration, favor fluid moving out of the capillary and into the interstitial space, are stronger or more predominant on the arterial end, whereas on the venule end, the forces that favor fluid moving back into the capillary are stronger or more predominant, okay? Now we're just kind of taking this face value. We haven't calculated this ourselves, which we will do in a minute. But what this points out is that something we already know. We need to see fluid moving in both directions as a part of the capillary function, right? So it's not just filtration happening right across or absorption happening right across, but we allow time for oxygen and nutrients to move out of the capillaries on the arterial end. And then we allow time for CO2 and other metabolites to move back into the capillary bed on the venule end, so those can be taken back towards the heart. Okay, so we need to see net filtration on the arterial end and then net absorption on the venule end. And so we're going to actually prove this to be true because we haven't calculated this ourselves. So we're going to actually net out those pressures we described and talk about how we can prove that net filtration happens here and net absorption happens on the other end. Okay, so let's start here. I'm going to draw a similar schematic to what we drew last time as far as our capillary and the interstitial space. So we've got net filtration pressures. Okay, otherwise known as NFP. Oops. So that's what we're going to be calculating out to prove to ourselves that what we just said is in fact true. Okay, so let's draw our tissue here once again. So we've got our tissue there. We've got our capillary. Let's actually draw this in black. We've got our capillary. okay? Remember, inside the capillary is the plasma. That's where one of our forces is being exerted. And then here in the interstitial space is our interstitial fluid, okay? Or tissue fluid or tissue space, okay? So let's actually label this out first. We got the arterial end. We've got the venule end. And then we also want to remind ourselves, this is the tissue. We also want to, in the corner here, remind ourselves of the, or describe rather, the forces that we have at play. So we said that pi representing the osmotic or oncotic pressure is a pull. Okay, just to keep this in the back of our head here. And then the large P, oops. Oh, geez, I can't draw today. Okay, the large P here representing our hydrostatic force is a push. Oh goodness, my pen is not cooperating, but this is a push, okay? So this should be push. So let's start putting in the values that we calculated. Now, does anyone remember which of our forces changed across the capillaries? So it was different on the arterial end and than it was on the venule end. So only one of our forces actually changed when we go from arterial to venule end. Anyone remember that force? So I'm seeing hydrostatic, which is correct. Anyone remember specifically which hydrostatic, when we have two hydrostatic pressures, one in the interstitial space, one in the capillary. So it's going to be that capillary hydrostatic pressure, right? So we're going to start with that one. So our large P capillary, that we said was 38 millimeters of mercury on the arterial end. And then by the time we get down to the venule end, it has decreased, which is a natural occurrence as you go from arteries to veins, right? The pressure drops off. So on the venule end, the pressure down here is now 16 millimeters of mercury, okay? And this is the only pressure that changes across the capillary. In terms of the capillary, the interstitial fluid capillary pressure, that's going to be, not capillary, excuse me, the interstitial fluid hydrostatic pressure, that's going to be 1 millimeter of mercury. We said it was pretty small. So the interstitial fluid hydrostatic pressure is about 1 millimeter of mercury. Oops, mercury. Okay, guys, please, this is why I ask you to please try to be on time to class. I'm gonna have to X out of my drawing here to admit someone in the waiting room. So please try to be respectful and mindful of our meeting time. Okay, there we go. All right. Okay, so we said the capillary hydrostatic pressure, 38 millimeters of mercury on the arterial end, 16 millimeters of mercury by the time we get on the venule end, and then the interstitial fluid hydrostatic pressure, really small, about 1 millimeter of mercury. Okay, let's look at our oncotic pressures now. So in the interstitial fluid space here, we have the interstitial fluid osmotic pressure. That we said was 0, right? We should not have proteins in the interstitial space. I'll talk about some of the clinical relevance of that coming up, but this should be 0 at all times. Okay, if we have this number beyond 0, we start to get into some problems and we start to get the edema and the swelling and so on. So this should be negligible. There should be no proteins here exerting a pulling force this way. And then we have the capillary osmotic pressure, which is 25 millimeters of mercury. Oops, I keep forgetting the H. Millimeters of mercury. okay? Let's put our arrows in so we remind ourselves of the direction of these forces. So this is going to be a push force out into the interstitial space. This will also be a push force out into the interstitial space. And then this is going to be this is a little misleading. Let me change this here. Let's put this way. And then this is going to be a push force back this way. As far as our oncotic or osmotic pressures, we said that they were pull forces. So this is going to be pulling fluid into the interstitial space. This is why it's really important that this is 0. And then this is going to be pulling fluid here into the capillary, okay? Everyone with me so far? Any questions so far? Any questions so far? So let's now start calculating this out for ourselves. So we're going to plug in these values. And again, we're aiming here to prove that what we said is true, that the arterial end movement here favors filtration, the venial end movement here favors absorption, okay? So let's calculate our net pressures out. Let's start with the arterial end first. Let's draw a little line down here. So at the arterial end, we know that when we calculate net filtration pressure, that's going to be net filtration forces minus our net absorption forces. Okay, and I'll put these in brackets because there's more than one. Okay, so let's start by identifying our net filtration forces. So someone's asking if the interstitial fluid osmotic pressure is 0, then it is pulling nothing out of the capillary. That is essentially correct. That's a good way to look at it, but we still want to take that value into account, although it's pulling nothing. That's correct. Okay. We said what forces would favor filtration? So first of all, filtration is movement of fluid from the capillary into the interstitial space. So which of our 4 forces, well, 5 in this case, forces favor that movement? Which of our 4 forces favor filtration? In other words, movement of fluid from capillary out into the interstitial space. I'll give you a minute to kind of think about this here, and then we'll plug these in. Okay, so I'm seeing the capillary hydrostatic pressure. Let's kind of reason that out. So the capillary or the capillary hydrostatic pressure, which is pushing fluid out into the interstitial space. So that is correct, right? So let's plug that one in. Our capillary hydrostatic pressure does favor filtration. And then someone's also saying the osmotic interstitial fluid, although they're kind of wording it incorrectly, that is also true. The interstitial fluid osmotic pressure also favors filtration, okay? Interstitial fluid osmotic pressure, right? Everyone agree with that? We can see how these 2 forces favor the movement of fluid from capillary out into interstitial space, okay? Okay, and I'm seeing some other chat messages that align with that as well. Excellent. Let's think about our forces that favor absorption now. So which forces favor the movement of fluid back into our capillary? Which of our forces favor that movement of fluid back into our capillary?
Osmotic capillary pressure, and then
Okay, yep, that's correct. So our capillary osmotic pressure, that's absolutely correct. And then our only other force that's left, right, which is our interstitial fluid hydrostatic pressure. Okay, oh, and I'm seeing that coming up in the chat, perfect. So our interstitial fluid hydrostatic pressure, again, think about where you're standing. We're standing in the interstitial space, and this is a push force, so it must be going back into the capillary. Same thing with our capillary osmotic pressure. Again, we're standing in the capillary. This is a pull force, so it must be pulling fluid back into the capillary as well. Okay, this is why it's so important to think about where you are and then think about the direction of that force. Okay, so we've identified our relative forces, so we can just simply plug our values in at this point. So we've got 38, remember we're dealing with the arterial end first, so we've got 38 plus 0 minus 1 plus 25. Okay, we can do some simple math here. This gives us 38. Oops, I can't write beneath here. Okay, we'll just plug it over on this side. I can't write any lower. So this is going to end up being 38 minus 26, and that equals 12 millimeters of mercury, okay? And so someone's asking where the 16 goes. Excellent question. So we're not looking at the 16 yet. We're starting with the arterial end calculation. So we're only looking at the pressures here. And then we're going to calculate the venule end in a bit. Okay, really good question. So 12 millimeters of mercury is our answer. And there are two ways that we know that this favors filtration. One, we can just simply look at the values, right? That the 38, which is the bigger value here, is the overall value of the filtration forces. The other sort of simple way of doing that is that just looking at the sign of the value. So because this is a positive number, 12 millimeters of mercury, we also know that this favors filtration. Okay, so on our arterial end, we have calculated and proved that this favors filtration. Okay, let's look at the venule end, and again, go ahead and calculate that. Oops. Okay, let's see, I got a question here. So if absorption was larger than filtration, would that cause us to swell up? So if it were larger than filtration right across, that would definitely cause swelling and edema. Yeah, I'm going to talk about some clinical examples in a bit, but this is why it's so important for this value to be 0. Okay, the bigger this value gets, the more we have fluid being, moving back into the back into the interstitial space, where it should not be. Remember, proteins here are going to exert a pulling force that will create a stronger force moving fluid in that direction. I'm seeing another question. If it was a negative number, would it favor absorption? Yes, absolutely correct. I'm glad someone made this connection. If it were a negative value, or if the absorption figures were larger than the filtration figures, which we're going to see here in a bit, that would indicate favoring absorption. So let's calculate the venule end here now. So on the venule end, we're going to plug in all of our same values, but we're just going to substitute the capillary hydrostatic pressure for, instead of 38, we're going to put 16 because that's what it is here on the venule side. All right. So NFP, once again, is our filtration minus absorption. Okay, we've already established which of these forces is which. So that was capillary hydrostatic and interstitial fluid osmotic for filtration, and then interstitial fluid hydrostatic and capillary osmotic for our absorption. Okay, and so just again, plugging these same values in, except swapping out the first value here. We're going to put 16 plus 0, and then the same 1 plus 25. Okay, And so we got 16 here minus 26, and we can already quickly begin to see that the filtration values are smaller than the absorption values. In other words, when we net this out, it's going to be a negative number. So negative 10 is our final net pressure here, and that we know favors absorption. Okay. And I apologize, I kind of ran out of room at the bottom here, but I hope that this is clear. Okay, I'm going to pause and see what questions you have about this so far. And then we're going to kind of add some meat on here in terms of the clinical relevance of all of this in a bit. So this is just proving what we just said, that our relationship we just described, we're at the arterial end of things. Our pressures favor the movement of fluid from the capillary out into the interstitial space. That's going to help send oxygen and nutrients into the tissues. And then when we get to the venue end, because the capillary hydrostatic pressure, which is kind of the main filtration force, has dropped off so significantly, we now have pressures, overall net pressure that favors reabsorption, okay? Let's see. Will the absorption value always be negative? Well, if the value is negative, it's always absorption. So kind of flip that relationship around. If the value is negative, it's always going to be reabsorption, as long as we keep this relationship, this equation the same. Filtration minus the absorption, as long as that becomes negative, it's going to be favoring fluid movement back into the capillary. Another question here, so the osmotic, interstitial fluid osmotic will always be 0. Yes, that's true. The interstitial fluid osmotic in our healthy, normal physiology should always be 0 or very, very negligible. It should not be raised. And to put the context there, we should not have proteins in this space. Proteins cannot go through our capillaries unless they're injured or unless there's another inflammatory response, which I'll talk about coming up. But proteins should not be able to escape and get into this space, right? They cannot go through the capillary. And so that's why this number is usually always 0. And that's why it's so important for it to always be 0, because then it starts exerting that osmotic pull, which now creates that fluid movement inappropriately into the interstitial fluid space. Okay.